So now, before the break, we did an example where we combine wide flange and box beam. I'm going to do another example. Okay. So example number 2. And example number 2 is, as I say, it's not a difficult problem also. Okay, I'll tell you why is it difficult. So example number 2. This is the question. Okay, and I'll show you the structure. Okay, I'll show you the structure. Okay, so example number 2. So this is the structure that is given. Okay. So knowing that it's very similar to what is before, but the structure is different, and I'll tell you why. So knowing that a given vertical shear causes a maximum shear stress of 75 megapascal in an extruded beam shown, okay, having the cross section shown, determine the shearing stress at the 3 points. Okay, so point C, point B, point A. Okay, so it specifies very specifically the 3 points indicated. Okay, so we're not going to calculate any other points. So what we see over here is this structure, it combines both thin wall and non-thin wall analysis. Okay. So let me tell you why, okay? So we will design our shear flow and our major web, right? And our major web flow this way. This is our major web flow. That's our major web. Right? And then it finish off here. It start off here. Okay. So this is our terminal 1, terminal 2, terminal 3, and terminal 4. Right? So if we were to sketch a centroid by observation, we are very sure that the centroid is here because it's axis symmetry. Okay. So point C and point B and C, if you look at over here, let me get rid of the. You can see that point C and point B should use wide flange, thin wall analysis. Okay, where you only have a single Q, right? Whereas at point A, right, non-thin wall analysis is used. Why? Because if you look at the thickness, either vertically is 60 or horizontally is what? Is 120. It cannot be thin wall for this case. You know that. Okay. So now we are going to use thin wall analysis for point C and point B, and then A. And this is a very similar structure as what we have in the previous problem. We are only given 75 megapascal as the maximum. Okay. And we don't know. We don't know which one is 75 megapascal? Is it point A? Is it point B? Or is it point C? Okay. So we are going to we're going to do thin wall analysis for point C and for point B first. Okay. So what we're going to do, we're going to apply the formula where shear stress is equal to Vy over Izz, right? Qz over T. And we are going to determine the location of tau max. And then we are going to find our Vy over Izz ratio from tau max location. Okay. So for this case, this is our Vy. Okay. So as I said, point A is non-thin wall. Point C and point B are thin wall analysis. Okay. 120 is just too big to be considered thin wall. So it's non-thin wall. Okay. So now we are going to find point C and point B. Okay, so start from point C, start from the closest location from the terminal. Okay, so we're going to find at point C, which is thin wall, white flange. Right, analysis, and it's going to be called Q. Right, so we're going to find. We're just going to consider this area because we're going to start from our terminal 1. Okay, so QZ, so if this is our transformation, Y and Z, and over here is our centroid. So I'm going to draw our centroid. Okay, so this is our centroid, right? So from here, we are going to okay, so from here, we are going to do our QZ at point C. So the width is 30, the depth is 10, the Y bar is 160, so 30, so it's 80 minus by 10 divided by 2. Okay, so this is width, depth, Y bar. Okay, so this is equal to 80 minus 10 divided by 2 times 10 times 30 is equal to 22.5 times 10 to the power 3, and this is in millimeter cube, or 22.5 times 10 to the power of minus 6 meter cube. Okay, so 22.5 is our is it wait 3 9 yes 6. Okay, then from here, wait, did I no sorry 22 wait 80 minus 5 times 10 times 30 22.5 to a 3 22.5 times, yeah, it's correct. So from here we can find the shear stress at point C is equal to Vy over Izz, and this is equal to 22.5 times 10 to the power minus 6, and the thickness is 10 millimeters. So this is equal to 22.5 power minus 6 to the power 10 power minus 3 is equal to 2.25 times 10 to the power minus 3 Vy over Izz. Okay. So next we're going to find point B, right? And we're also going to use thin wall, white flange analysis. And it's also going to be Q. So the area that we're going to consider now is this entire area over here, okay, including the first part of QZC. Okay, so now to find the first moment of area about the z-axis at point B, we are going to include the 22.5 times 10 to the power 3 plus by the width of 20, the depth of 40, which is 40 plus 10 of 50, and the y bar will be 30 plus by 50 divided by 2. Okay, so this is equal to 22.5 times 10 to the power 3 plus 30 plus by 50 divided by 2 times by 50 times by 20 is equal to 55 times 10 to the power 3. So 22.5 plus by 55 is equal to 7.5 times 10 to the power 3 millimeter cube, or 77.5 times 10 to the power minus 6 meter cube. Okay. So the shear stress at point B now will be equal to Vy over Izz. Okay. And then you have 77.5 times 10 to the power minus 6. We are going to divide by a thickness by 20 times 10 to the power minus 3. And we don't need to include 2 because it's just all these are single Q. It's white flange. 77.5 power minus 6 divided by 20 power minus 3 is equal to 3.875. 3.875 times 10 to the power minus 3 Vy over Izz. So now we realize at point B is where the maximum shear stress is. Now we know that it is actually at point B. Okay. Anyone, any questions so far regarding this? Are you okay? Anyone having issue visualizing the first moment of area?
How do we know that C and B it's a thin wall analysis again?
Because of the thickness. Okay, this is 10 millimeters. This is 20, right? And then at
Yeah.
point A is 120. It cannot be thin wall.
Yeah. So what's the biggest until you can do a thin wall analysis?
As I said, this example is pretty complex. So in the test, I will tell you, but in real engineering practice, you check both. You calculate
Okay.
both using thin wall and non-thin wall. Okay.
Okay. All right.
Yeah,
Thank you.
yeah. But in if this question were to come out in the term test, I already show you how to do it already. For example, if you've not seen that question before, and I will tell you use thin wall or use non-thin wall. Okay. Right. So if we look at point C now or point A, we know that the point B will have a higher stress than point C, right? So now we are going to find at point A. Okay. So point A, we're going to apply non-thin wall analysis. Okay, we're going to apply non-thin wall analysis for this. And the thickness now is equal to 0.12. Okay, that's the thickness that we're given, and that's the thickness we're going to use. Okay, so we are going to find QZ